Welcome! In this session, we'll explore LeetCode problem number 816, ambiguous coordinates. This is a fascinating string manipulation problem that requires us to generate all possible valid coordinate representations from a given input. Stick around as we dive into the concepts, approaches, and key insights for solving this problem. In this problem, you are given a string S that represents a set of coordinates. This string is made up of digits and is enclosed within a pair of parentheses, like 123. Your task is to generate all possible valid coordinate representations from this string. A coordinate representation is a pair of two numbers, written as x, y, where both x and y are valid decimal numbers. To form these coordinates, the string must be split into two non-empty parts, representing x and y. Each part must satisfy certain rules to qualify as a valid decimal number. For instance, while a decimal point is allowed, the number cannot have leading zeros unless it is just 0, and trailing zeros after a decimal point are not permitted. Additionally, the input string will always have at least 4 characters, including the parentheses, and your goal is to return all unique valid coordinates derived from the string. Now, the output of the problem is expected to be a list of strings, where each string represents a valid coordinate in the format x, y. To illustrate this, let's consider an example. If the input string is 123, the output would be a list containing the coordinates 1, 23, 12, 3, 1.2, 3, 1, 2.3. Here's why these outputs are valid. The original number is 123. By splitting it into two parts and optionally inserting decimal points, we can create the valid coordinates. For example, splitting as 1 and 23 gives the coordinate 1, 23, which is valid because both parts satisfy the decimal number rules. Additionally, we can split the string 123 in other ways to produce more valid coordinates. For instance, splitting as 12 and 3 forms the coordinate 12, 3. Inserting a decimal point into the first part, we can split as 1.2 and 3 to form the coordinate 1.2, 3. Similarly, placing the decimal point in the second part, splitting as 1 and 2.3 results in the coordinate 1, 2.3. Each of these pairs is valid because they adhere to the rules for decimal numbers. Now, let's explore another example to understand how leading zeros influence the formation of valid coordinates. For the input string 0, 1, 2, 3, the output includes coordinates like 0, 123, 0, 12.3, 0, 1.23, 0.1, 23, 0.1, 2.3, 0.12, 3. Here, the original number is 0, 1, 2, 3. And we can split it in several ways while carefully handling leading zeros. For example, splitting as 0 and 123 forms the coordinate 0, 123. Similarly, inserting a decimal point in the first part gives splits like 0.1 and 23, resulting in 0.1, 23. We can also place the decimal point in the second part, splitting as 0 and 12.3, which gives 0, 12.3. Each combination is valid as it respects the rules for decimal numbers. Finally, let's discuss some constraints and edge cases. The length of the string S will always be between 4 and 12 characters, inclusive. The string is guaranteed to consist only of digits wrapped in a pair of parentheses, such as 123. When handling edge cases, consider strings with all zeros inside the parentheses, like 000. These may not produce any valid coordinates because the rules for valid decimal numbers would be violated. Similarly, strings with leading zeros, such as 000123, require careful handling to avoid invalid representations. Remember, no integer can start with leading zeros, and no decimal number can have trailing zeros after the decimal point. These constraints and edge cases ensure that your solution generates only valid and unique coordinate representations. To solve problem number 816, we need to generate all valid coordinate representations from a string formatted as 1234. The goal is to produce all possible x and y coordinate pairs, where each coordinate can be an integer or a decimal number. One approach to tackle this problem is the brute force method. The idea here is to explore all possible ways to split the string into two parts, representing x and y. For each substring, we systematically generate all valid numbers by inserting decimal points at every position and checking if the result is valid. Once we have valid x and y values, we combine them into coordinate pairs. While this method is easy to implement, it comes with a significant drawback: it generates many invalid combinations, which makes it computationally expensive. Specifically, the complexity of O(n) cubed arises from iterating over all splits and processing each part with nested operations. This inefficiency is something we aim to address with an optimized approach. To improve upon the brute force method, we use an optimized approach that incorporates validation rules to quickly discard invalid substrings. These rules ensure that numbers generated from the string meet specific criteria. For example, a valid number cannot have leading zeros unless it is a standalone zero. Similarly, decimal numbers cannot have trailing zeros, and they must always include at least one digit on either side of the decimal point. Using these rules, we refine the process. First, we remove the parentheses from the input string. Then, we iterate over all possible split points to divide the string into x and y parts. For each part, we validate the substring according to the rules and generate only the valid numbers. Finally, valid x and y pairs are combined into coordinate strings. By eliminating invalid cases early, this approach significantly reduces unnecessary computation. The time complexity improves to O(n) squared, as the validation step efficiently prunes invalid substrings. While this method is more efficient, it requires careful attention to ensure the validation logic handles all edge cases correctly. We selected the optimized approach with validation rules as our strategy because of its clear advantages. It dramatically reduces the number of combinations to evaluate by discarding invalid substrings early in the process. This makes the solution not only more efficient but also easier to manage and debug. The validation rules are straightforward to implement, and they help maintain a balance between clarity and computational performance. A key insight, or aha moment, was recognizing that a significant number of substrings can be deemed invalid at the outset, for example, numbers with leading or trailing zeros. By focusing on this validation step, we reduced the problem's complexity and avoided unnecessary processing. Additionally, understanding that the solution requires only valid combinations of x and y pairs, without concern for their order, helped simplify the implementation further. This approach strikes a practical balance, ensuring efficiency without overcomplicating the solution. When comparing the strategies, the brute force approach stands out for its simplicity but is hindered by inefficiency due to the generation of many invalid combinations. On the other hand, the optimized approach strikes a balance by leveraging validation rules to prune invalid substrings early, improving both efficiency and clarity. However, this method does require careful handling of edge cases, such as dealing with numbers like 0.0 or 2000. There are alternative optimizations, such as pre-processing the string to identify valid partitions more effectively, but these would add complexity with minimal performance gains. In terms of complexity, our chosen approach operates with a time complexity of O(n) squared, driven by the splitting and validation processes. The space complexity is O(n), which accounts for intermediate results during processing. Overall, this optimized method provides a practical and efficient solution to the problem while maintaining manageable complexity. The problem ambiguous coordinates revolves around generating all valid coordinate pairs from a string of digits enclosed in parentheses. For instance, if the input is 1234, we need to identify coordinate representations like 1.2, 34, or 12, 3.4 by exploring all possible combinations. The main challenge is to correctly interpret the string while maintaining valid number formatting. This means ensuring there are no leading zeros unless the number is a single digit, and avoiding trailing zeros in decimal representations. The first step in our approach is to parse the input string. We extract the digits inside the parentheses, ignoring the parentheses themselves. For example, given the input 1234, we isolate the substring 1234 for further processing. This forms the core input for subsequent steps in the algorithm. The next part of the algorithm is to define a helper function that generates valid numbers from a given string. This function, called generate_valid_numbers, handles two cases. For integer representations, the function ensures that numbers either lack leading zeros or are single digits, so a string like 1 foot is invalid, but 1 is valid. For decimal representations, the function inserts a decimal point at every possible position within the string, starting from index 1 up to len (s)(1). For example, the string 123 would produce potential decimals like 1.23 and 12.3. However, decimals must meet additional criteria. There should be no leading zeros in the integer part and no trailing zeros in the decimal part. For instance, 1.23 is invalid because of the leading zero, and 1.230 is invalid because of the trailing zero. With this helper function, we can ensure that only valid numbers are produced. Once we have this, we move on to splitting the string into two parts. By iterating over all possible split points, we divide the string into two non-empty substrings, left and right. For instance, splitting 1234 at index 1 would give 1 and 234, splitting at index 2 produces 12 and 34, and so on. These splits lay the groundwork for pairing numbers to form coordinates. After splitting the string into two parts, the next step is to generate coordinate pairs. For each split, we use the helper function to generate all valid numbers from the left substring and all valid numbers from the right substring. Once we have these valid numbers, we form coordinate pairs by combining each number from left with every number from right. For instance, if left generates the numbers 1 and 1.2, and right generates 34 and 3.4, the resulting coordinate pairs would include 1, 34, 1, 3.4, 1.2, 34, and 1.2, 3.4. This process is repeated for all possible splits of the string. Finally, we collect all valid coordinate pairs from every split and return them as the final result. This ensures that we fully explore all combinations while adhering to the constraints of valid formatting. There are several key insights that make this algorithm both correct and efficient. First, handling leading and trailing zeros is crucial. Numbers with leading zeros are only valid if they are single digits, which means 1 foot is invalid, but 0 is allowed. Similarly, decimal numbers must avoid trailing zeros, so 1.230 is invalid, but 1.23 is valid. Second, the approach is efficient in its completeness. By iterating over all possible split points, we ensure that every way of dividing the string is considered without redundant computations. Lastly, the modular design of the algorithm is worth highlighting. Using a helper function to handle the generation of valid numbers simplifies the implementation and makes the code easier to debug. This modular approach also allows for flexibility, should we need to extend or adapt the algorithm in the future. The data structures used in this algorithm are straightforward but effective. Strings are the main data type used to manipulate the input, generate substrings, and create different number formats. Lists play a crucial role in storing valid numbers produced by the helper function, which makes it easy to perform operations like Cartesian products. Speaking of Cartesian products, the combination of valid numbers from the left and right substrings is essentially a Cartesian product operation. This is achieved using nested loops, where every number from one list is paired with every number from the other. These simple yet powerful data structures ensure that the algorithm remains efficient and easy to implement. To ensure the robustness of this algorithm, we must account for several edge cases. For example, if the input string contains only a single digit, such as 1, there are no valid splits, so the result should be empty. Strings with leading or trailing zeros, like 010 or 1230, must be handled carefully to avoid producing invalid numbers. Additionally, it's important to verify that all valid splits are considered, regardless of the string's length. In terms of complexity, the algorithm has a time complexity of approximately n cubed, in the worst case. This is because for a string of length n, there are n1 possible splits, and the generation of valid numbers involves iterating over all substrings. The space complexity also scales with n cubed, as the storage requirements are proportional to the number of valid coordinate pairs generated. Together, these considerations ensure that the algorithm is both efficient and complete, while addressing all potential edge cases. Here, we are implementing the solution for the ambiguous coordinates problem. The function ambiguous coordinates begins by defining a helper function called generate_possible_numbers. This helper function takes a string s and generates all valid number representations from it. First, we check if s can be used as a single integer without a decimal. This is valid if it doesn't begin and end with 0 simultaneously, except for the case where s is just a single 0. If valid, we add it to the results list. Next, we handle numbers with decimal points. By iterating through the string, we split it into two parts, left and right. We ensure that the left part does not start with 0 unless it's just 0, and the right part does not end with 0. If these conditions are met, we combine the two parts with a decimal point and add the result to the list. After defining this helper function, we proceed to process the input string by removing its outer parentheses. Then, we iterate through potential split points to divide the string into two parts, left underscore part and right underscore part. For each split, we generate all possible valid numbers for the left part using the helper function. We then generate all valid numbers for the right part using the same helper function. With both left underscore candidates and right underscore candidates prepared, we use nested loops to combine every candidate from the left with every candidate from the right. For each combination, we format these numbers as a coordinate pair in the form of left, right, and add it to the results list. Finally, after processing all possible splits and combinations, we return the complete list of valid coordinate pairs as the output. Here, we start by defining the method Ambiguous coordinates, which takes a string s as input. The first step is to remove the outer parentheses from the string, as they're not part of the coordinates themselves. Next, we determine the length of the string and initialize an empty list called result to store all the valid coordinate combinations. The main logic involves a loop where we split the string into two parts at every possible position. For each split, the left part represents the substring before the split point, while the right part represents the substring after it. These parts are then passed to the helper method generate possible numbers, which generates all valid numerical representations for each part. Once we have the valid numbers for the left and right parts, we combine them in the format left, right, and add them to the result list. This ensures we systematically explore all potential coordinate pairs. The helper method generate possible numbers is designed to generate all valid representations of a number, including those with and without decimal points. First, we initialize a list results to store the generated numbers. We then handle the case for single integers without decimals. Here, we check if the string does not have leading or trailing zeros, unless it's a single character 0. If the condition is met, the number is added to the results list. Next, we consider numbers with decimal points by looping through all possible decimal positions. For each split, the left part represents the integer portion, and the right part represents the fractional portion. We ensure the integer portion does not have leading zeros unless it's 0, and the fractional portion does not end with a 0. If these conditions are satisfied, we concatenate the left and right parts with a decimal and add the result to the list. This method ensures that only valid representations are included, which are then returned to the main function. To start solving this problem, we begin by pre-processing the input. Given the string 123, the first step is to remove the outer parentheses, leaving us with 123. Next, we consider all possible ways to split this string into two parts. For example, splitting at index 1 gives a left part of 1 and a right part of 23. Similarly, splitting at index 2 gives a left part of 12 and a right part of 3. Once we have these splits, we generate possible valid numbers for each part. Looking at the left part 1, it's a single-digit integer, which is valid, and no decimals are possible in this case. Therefore, the result for the left part 1 is simply 1. Now, for the right part 23 foot, we also generate possible valid numbers. As a whole number, 23 foot is valid. Additionally, we can insert a decimal point to get 2.3, which is also valid. Therefore, the possible numbers for 23 foot are 23, 2.3. With the left part producing 1 and the right part producing 23, 2.3, we can now combine these results to create coordinate pairs. This gives us 1, 23, and 1, 2.3. Repeating this process for the other split, where the left part is 12 and the right part is 3, we find that 12 can produce 12, 1.2, and 3 results in 3. Combining these, we get coordinates 12, 3, and 1.2, 3. After combining all the results from the different splits, we arrive at the final output for this example. The possible valid coordinate pairs are 1, 23, 1, 2.3, 12, 3, 1.2, 3. Now, let's move on to another example, where the input string is 00011. We start by pre-processing the input, removing the parentheses to get 00011. Next, we explore all possible splits of this string, such as 0 and 0011, 2000 and 011, 000 and 11, or 0001 and 1. For the left part 0, it's valid as a single integer, so the result is 0. Looking at the right part 0011, we attempt to generate valid numbers. However, as a whole number, it's invalid due to leading zeros. Similarly, adding a decimal still results in numbers with leading zeros, which are not allowed. Therefore, the result 40011 is an empty list. This means the split 0 and 0011 doesn't yield any valid coordinate pairs. Focusing on other splits, we find that the split 0001 and 1 produces valid numbers. The left part 0001 can be written as 0.001, and the right part 1 is valid as is, giving us coordinate pairs 0.001, 1. This becomes the final output for this example. Next, let's consider the input, 100. After removing the parentheses, we are left with 100. We evaluate all possible splits of the string, such as 1 and 2000, or 10 and 0. For the left part 1, it's valid as a single integer, so the result is 1. However, for the right part 2000 foot, it's invalid as a whole number due to trailing zeros, and adding a decimal is also not allowed because of the trailing zeros. Therefore, 2000 foot produces no valid results. Looking at the other split, where the left part is 10 and the right part is 0, we find similar issues. The right part 0 is invalid due to trailing zeros, leaving no valid combinations for this input. As a result, there are no valid coordinate pairs possible for the input, 100. The final output for this example is an empty list, represented as. In analyzing the time complexity of the ambiguous coordinates function, we start by breaking down the key operations. First, we process the input string s, where removing the outer parentheses is a straightforward operation that takes n time. Next, we consider splitting the string into left and right substrings. This involves iterating through all possible split points, which results in n1 iterations. Now, for each of these substrings, we call the generate_possible_numbers function. This function handles the generation of valid numbers, both integers and decimals. For a substring of length k, it iterates over all possible decimal placements, which requires k1 iterations. Additionally, validity checks, such as ensuring there are no leading or trailing zeros, also take k time per number. This means that for a substring of length k, the overall complexity of generate_possible_numbers becomes k squared. These steps form the foundation of our time complexity analysis. Now, let's focus on the step of combining results. For each split point, we generate possible numbers for the left and right substrings. If the lengths of the left and right substrings are I and ni, respectively, the Cartesian product of their possible candidates determines the number of combinations. Let's say there are L candidates from the left and R from the right. The Cartesian product involves L** R combinations. Since generating candidates for the left and right substrings involves I squared and open parenthesis n minus I close parenthesis squared operations, respectively, the combination step's complexity is proportional to L** R. However, L and R are bounded by I and ni. Putting all of this together, the overall time complexity in the worst case is n cubed. This comes from processing each split point, where substring lengths can approach n, leading to n squared operations per substring and n splits. In the average case, the complexity improves slightly because the number of valid candidates is typically smaller. To understand the space complexity, let's consider the major components of the function. First, there's the storage required for the output. The result stores all valid coordinate combinations, and in the worst case, there can be n squared valid pairs. Since each pair consumes space proportional to its length, or n, per coordinate pair, the total output space becomes n cubed. Next, we have temporary storage in the generate_possible_numbers function. For a substring of length k, this function temporarily stores all valid candidates. Since generating these candidates takes k squared space, and this process is repeated for both the left and right parts, temporary storage can grow to k squared for each substring. Finally, there is no recursive call stack in this function, so no additional space is consumed there. As a result, the total space complexity is dominated by the output size, leading to a worst-case bound of O, n cubed. In practice, the average case depends on the number of valid coordinates, but it typically remains below this worst-case limit. Let's compare the optimized approach with a naive or brute force method. A brute force approach would involve generating all possible coordinate pairs by inserting decimal points at every possible location in the string. This would result in an exponential number of combinations, specifically, 2 to the power of n, due to the large number of decimal placements. Such an approach quickly becomes infeasible as n grows. On the other hand, the current optimized solution significantly reduces the complexity by focusing only on valid candidates. The generate_possible_numbers function filters out invalid numbers upfront, such as those with leading or trailing zeros, and only processes valid substrings. This optimization reduces the overall complexity to O, n asterisk n cubed, in the worst case. While this is still polynomial in nature, it is far more efficient than the brute force approach, making the solution scalable to larger inputs. To summarize, the time complexity of the solution in the worst case is O, n to the power of 4, which arises from the nested loops required for substring processing and candidate combination. In the average case, the time complexity is slightly better than O, n to the power of 4, because fewer valid candidates are typically generated. For space complexity, the dominant factor is the storage required for the output, which leads to a worst-case bound of O, n cubed. Temporary storage and the absence of a recursive call stack contribute minimally compared to the output size. The mathematical proof for the time complexity stems from the nested operations, generating candidates with O, n squared, complexity, combining results proportional to the Cartesian product of candidates, and summing over all split points, which results in the final bound of O, n asterisk n cubed, equivalent to O, n to the power of 4. This breakdown confirms the efficiency of the optimized solution compared to the brute force approach. When working on ambiguous coordinates, there are a few common mistakes to watch out for. One of the most frequent errors is forgetting to handle leading zeros properly. For example, while 0.1 is a valid decimal number, 0.1 is not allowed as an integer because whole numbers cannot have leading zeros. Another mistake is misinterpreting the format of the input string. Remember, the input always comes with parentheses, so you need to strip those off before you start processing the coordinates. Decimal placement is another tricky area. Placing a decimal at the beginning, like 0.123, or the end, like 123, makes the number invalid. A valid decimal must always have digits on both sides of the decimal point. Lastly, it's easy to overlook all possible ways to split the string. For instance, if the input is 1234, you need to consider splits like 1234, 1234, and so on. Missing any of these can lead to incomplete solutions, so ensure you explore all valid combinations systematically. Edge cases are another important area to consider. Short strings like 10, or strings with repeated digits, such as 100, often have fewer valid representations, and skipping these edge cases can lead to errors. Observing patterns is critical here. For instance, recognizing that valid numbers can either be integers or properly formatted decimals helps you apply the correct rules consistently. This problem also relies on iterative split thinking, where you systematically divide the string into two parts in all possible ways, validating each part to ensure correctness. Balancing efficiency with completeness is key. While a brute force approach may explore every possible split, it can be inefficient. Optimizing your algorithm to skip invalid combinations early reduces unnecessary computations. Debugging is also crucial. Small, simple examples like 123 are great for verifying your logic and ensuring that all splits and combinations are handled correctly. This problem shares similarities with several other LeetCode challenges. For example, LeetCode 93, Restore IP Addresses, also involves splitting a string and validating each part. Another related problem is LeetCode 22, Generate Parentheses, which combines combinatorics and string generation. LeetCode 46, Permutations, focuses on generating all valid permutations, while LeetCode 131, Palindrome Partitioning, is another string splitting problem that requires validation of each split. When approaching this problem, you can choose between different strategies, each with its own trade-offs. The brute force approach involves generating all possible splits and validating each one. While it's straightforward to implement, it's not very efficient because it spends time checking invalid combinations unnecessarily. A more refined alternative is to validate splits as you generate them. This reduces redundant checks and improves runtime, though it requires slightly more complex implementation. Another approach worth considering is recursive backtracking. Here, you use recursion to systematically explore all possible splits, validating each segment at every step. This method can be particularly elegant for small input sizes, as it naturally handles combinations and validations in a structured way. However, the downside is that recursive backtracking can become slower for larger inputs due to the overhead of recursive calls. It's important to weigh this trade-off depending on the constraints of the problem. For small to moderate input sizes, this approach can be a clean and intuitive way to solve the problem, but for larger datasets, you may need to lean towards more iterative or optimized solutions to ensure efficiency. Great job making it to the end. We reviewed the key concepts and approaches for solving ambiguous coordinates. Remember to practice parsing and validation techniques, as they're crucial for problems like this. If you enjoyed this session, don't forget to like, share, and subscribe. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!